Okay, so in this video clip, I'm going to run through, in fact, the Tian 1993 binomial option pricing model used for pricing American options. And we're going to use a lattice framework for that option pricing. Now, there's a link there to some discussion around the performance of the Tian model, Leisen and Reimer, and we've introduced also into that paper intelligent lattice search. But just in terms of basic overview of the Tian model, I'm going to run through here a few examples in R, MATLAB, VBA, C++, Python, and I'm going to start with R. And the model is it's based on largely the Cox-Ross-Rubinstein approach, but we can adjust the parameters for P and 1 minus P and the jump parameters U and D by making use of these mathematical formulae. And I leave that for you to read through. So basically, if we're to run the Tian model in R, there is a function. I've set this up here in Google Colab. There is a function that's available in the fOptions R package, and that was implemented by Diethelm Wuertz, and it runs the model. I've checked, it seems to be correct. So to execute that, just to run the model here, we load in, it is an R function, and we're using R code here, but normally Google Colab will only run Python, but we can also run R, C++, MATLAB as well. Here I'm going to run R. To enable that, we have to use this magic R command, and thereafter any R code that we have, put in this double percentage sign, and then R in addition. And then afterwards, the function will run natively. Now I have the link here to the function. We can just copy that and just take a look at the source here. That might be important to point that out. Control V, and we run, and we have different implementations. So we have CRR, Jara Rud, and the Tian model, and we can come down to the functions. So let's take a look at the Tian model. It's here, and it's implemented by Diethelm, and so that's basically it. And so we take that and we've copied it into Google Colab here, and I put in addition to that the parameters, it's an American call, the stock price, the exercise, the time period, the risk-free rate, the cost of carry, which is, if you like, the risk-free rate minus the dividend yield. So here the dividend yield is 7%. So 7 subtracted away from 3 gives us that -4. The 0.2 is the volatility, and 500 here is the number of steps in the tree. So if we execute that, that'll execute actually quite fast. If we raise it up to 5,000, put in another 0 there and execute, it'll take a little bit longer, obviously, and you have 5,000 by 4,999 divided by 2 nodes. Okay, so that's taking a little bit longer, but the result that we should get should approximate to a 15, should approximate to true, and we have a measure of true here. Let's just point that out. As a reference, I'm using Broadie and Detemple 1996, and they point out if you go using Cox-Ross-Rubinstein, if you run a 15,000 step tree, then you approximately get true. And Amin and Khanna 1994 pointed out that discrete time models do converge to continuous time models. So we have a set of parameters here that I've taken from the Detemple, Broadie and Detemple paper, and that should yield us, if we take a look here, taking those parameters, the stock price 100, the exercise 100, the risk-free rate of 3%, the dividend of 7, the volatility of 20, maturity of 3 years, a true value here would be 9.066. Now we're getting 9.058 on that 5,000 step tree. So, you know, we're basically at true there. We could go down to 500 steps. Obviously, that's a little bit faster. Should be a lot faster, in fact. And we're getting 9.063. So the Tian model is quite a good model. It's for a review of the model and under what conditions it performs well. You might click the link here. We've set that up using intelligent lattice search, and that boosts the performance of the model, all else being equal. But the Tian model is a relatively strong model for running option pricing in terms of its performance relative to peers. Okay, so I can copy this code. We can set this up in RStudio. And if I go in, if I just open up RStudio, file, new file, R script, we'll paste in that snippet of code. Now we shouldn't have this double percentage R here. That's only for Google Colab. If I run that snippet of code using 500 steps, I should get the value of the 9.0638, and I do. If we raise that to 5,000 and run again, this is not going up to a server, this is on my own machine. 5,000 steps is a lot of nodes in the tree, probably well in excess of 1 million, right? Nodes here, so it's 5,000 by 4,000 divided by 2. So we're talking a lot of nodes, 9.0658. Okay, so that tallies with the results we got in Google Colab. And it's also, we can see it's in the vicinity of what's mapped out in Broadie and Detemple for true. Okay, to get a more exacting figure, we could go up to 15,000. Let's just try that here, 15,000. And I might pause here. Note the time here is 12:12. I'm going to run that in Google Colab. Now it won't be. This will be quite a take quite an amount of time to run. We'll check when it's executed completely. So I'm going to pause here. Okay, so you can still see this estimation is still executing, and it's 12:14. Let's just pause again and see when it estimates. Okay, so it's fully estimated here now, and we're getting 9.0659464. So we're in that vicinity of the 9.06, and it took about, well, it's now 12:15. So it's not instant. When you go up to 15,000 steps, it's actually going to take quite a bit of time to run these estimations. But Google Colab is actually quite fast. So in that regard, the performance is not bad. But 500 steps looks okay. And we're getting 9.063, which is in the vicinity of true. So let's stop here, and then in the next video I'll explain the MATLAB implementation of the Tian model.